This is Elaine McCormick for Lab 5, Motion of Falling Objects. I observed a Band-Aid box which I dropped and it fell quickly in the negative y direction. Also, I observed a paper which fell slowly in the negative y direction. The main result of this lab is that air resistance causes the objects to fall at different speeds. I found this by looking at our main objectives, which are to compare the falling objects' velocities, find the terminal velocity, and compare the difference between air resistance to weight ratios of the object. So you can see here, my first step in Tracker was to show the videos where I dropped the two objects. This is my Band-Aid box, which falls quickly. You can see that I set the axes so that the object falls in the negative y direction. I set the length scale for the video, which 0.08 meters, which is the length of my Band-Aid box also. I cut the video so that you can only see the box when it is falling and increasing in speed as it falls quickly for 0.4 seconds, and you can see that the center mass is recorded as it falls to show the position as well as its average velocity. This next video is the paper fall, which falls slowly. I did the same thing, set the axes so that it falls in negative y direction. I set my calibration stick to the length of the paper, which is 0.21 meters, and that's the scale for the video, and then I chose about a half a second length of the total video in which the paper is falling in the negative y direction and recorded the point mass during that whole time. The average location is marked, and I got that data, and then from there I was able to make models in VPython. So you can see my first model right here. This is only affected by gravity. You can see that this is my mass for initial conditions of my Band-Aid box. The position is the origin. There's no initial velocity since I just dropped it. It has a small time step. When I go down here, I used Newton's second law and set for this one the F net equal to the force of gravity, which is labeled up here. And then I put an arrow so you can see the only force acting on the object is gravity. And I'll run this, and you can see it falling quickly due to only the force of gravity. So next, I created a model to show the effect of drag on an object. So same thing, initial conditions, but the mass of the object, which is lighter, so we put that in there. Small time step, no initial velocity, and this time we have the force of drag included in here, which is proportional to just the velocity. And so you can see that when I run it as a blue arrow putting in the positive y direction, which slows down the object as it falls. Theirs are kind of small, but you can see them right there. Okay, so then I took this and put it in Excel to compare my two models. You can see that I have the first one is my rapidly falling object, which is my Band-Aid box in the red, and then my gravity model in the blue, and they both fall with increasing speed, which just continues for the whole length of the video. Next, I have my slowly falling object and my drag model, and so you can see that both of these reach their terminal velocities due to the drag force, and so the paper was in red and the drag model was in blue. So what does all of this mean? Okay. What does all this mean? We use the model to imitate the drag force, and the force is proportional to the velocity in the opposite direction from Newton's second law. You can see when we made the paper with the drag that it falls slowly to reach its terminal velocity, whereas the Band-Aid box with its drag falls much more quickly to reach its terminal velocity. These are predicted by my models and shown throughout here. And you can see those on the videos. You can see that the forces equal each other, so the pushes and pulls will stay at 0 because the drag force is proportional to the velocity, and the velocity is due to the gravitational force, and those are the only two forces acting on it as stated by Newton's law. So, what if? My Band-Aid box dropped slowly? So we used a model to examine the object's velocity with a function of time in the case where the object is thrown downward initially instead of dropping it from rest. In this way, it'll have initial velocity of -5 in the y direction. So as you can see, I have two of these, one with drag and one without drag. So my, yeah, there we go. Okay, so my slowly moving object, the paper, with drag and the initial velocity you can see as it falls here, and then reaches its terminal velocity quicker because it has initial velocity, so it starts, and then initially it reaches its terminal velocity there. And then if you look at it with no drag and initial velocity, you can see that it still continues to increase instead of reaching its terminal velocity. Same thing with the Band-Aid box, except for that it falls more quickly because it weighs more, which increases the velocity due to the gravitational force. The velocity is the slope of the position versus timeline, so that's what I'm pointing out in these two. And you can see that by overall adding an initial velocity, the objects reach their terminal velocity quicker when they have the drag force. And if they do not have drag force, they just keep increasing because they have no force opposing the velocity and due to the gravitational force. So, overall, our chief results is that drag is related to terminal velocity because it creates the terminal velocity. There's no drag. The object would keep increasing due to the gravitational force. Velocity is also related to air resistance because your air resistance is related to the drag. Air resistance, drag, same thing. The pushes and pulls are always equal to 0. This F net is equal to 0, Newton's law. We saw that with all of our objects. And then finally, the drag force is opposite to the force of gravity and free fall. They go in opposite directions. You saw that in my model and throughout my whole results.